So in our case, we're saying check the database for a storage, check the database for a token. If we don't have one, we'll call the next decorator. In our case, will just be the API repository. And in this case, after we've called it, we've got the token back. The storage dependency can then save the token in our database again, so the next time we hit it, it will be there and valid, and then we can return it. The important point to note is that this instance of access token repository that we pass in could be any implementation we like. So if we want to add additional decorators to our chain, we can do that. So here's what the usage of that code would look like. We have to instantiate a few different things, wire things together. This is an example of Solid meaning having to write a bit of code. Solid tends to put the burden on the calling code. This is an example of that. So we're going to set up all the dependencies. And then what I think is really nice and really simple is that the client code, okay, does have to deal with wiring together these dependencies, but then you can just call one method and it gets a token back. And it doesn't need to know anything about what's happening underneath that. It doesn't know that there's any decorator pattern involved there. It doesn't know that it's getting a token from storage or from the API. It doesn't care. It doesn't need to know. So if we wanted to add an additional decorator here, let's say if we wanted to log every time we were hitting the API to request an access token, we can add a new implementation of our repository and sandwich that in between the different layers of our decorator set. The final pattern I want to briefly mention, I don't have time unfortunately to go into any detail on this, is the observer pattern. This is another way you can keep your classes open for extension. If we think back to that controller example, where we'd refactored it out into a service class, we could make that class more open to extension by using the observer pattern. All I can say is this is a really interesting and useful pattern. If you've ever used frameworks, event subsystems, they tend to use a version of the observer pattern, and there's some really great articles out there that you can go away and read. I would recommend that. There's a good section in that book as well. Don't mention it. So on to the L of Solid, which is the Liskov substitution principle. Liskov substitution principle was formulated by a woman called Barbara Liskov. She was an awesome lady. She was the first woman in the US. His article, Uncle Bob talks about a strong correlation between this type which wasn't specific enough for their use case. So, like I mentioned, I want to talk specifically about ISP. We talk so long about each individual one. There's a guy called Dan Aykroyd who did a really good talk about this at PHP Northwest last year. The video's not online yet, but the slides are, so I've got a link to those. And so he goes into a bit more depth than I can about this time. So here's an example of ISP at work. Literally at work. This is adapted from something we did. So at the end of last year, we were working on an application which had pages, which had lists of things on it. So we had things like lists of users, lists of clients, lists of projects, that kind of thing. And so there were going to be loads and loads of items, hundreds of items. So users needed a way to filter those lists and find what was actually interesting to them, what they needed to use. So we had to include various search options at the top of each page. So we had types like drop down. So if we wanted to search for projects for a certain client, we had a select with the client names in them. Free text. So if we wanted to search for a project name, we had a free text field. And date ranges. So if we wanted to find projects created within a certain page, there'd be a couple of date pickers that they could use. So we decided the way that we could implement this would be to use our friend the decorator pattern and the composite pattern. And we created this interface called filter. And the idea would be that each of those types of filter, date range, free text, drop down, etc., would have its own implementation of this interface. And additionally have a collection class which will bundle all words together. So this interface has a method called build query from, which has two request, which is KPHP's HTTP request object. And the idea would be that when a user filled in the form, they had posted would be populated in the query string, and you could grab their search data from the query string. So the request object in KPHP has a query method, so we can just grab what's coming from the query string using that query method. So it's slightly confusing called query. This is a different kind of query. This comes from KPHP's ORM, so this is a database query. And we can do each filter, we can look at what users actually search for and decide whether we need to adjust our database query accordingly. So here's what the filter collection would look like. We have a method add, where we can add filters in. And then in the query from implementation, we can loop over each of those filters. We can decorate the query object by passing it in along with the request. Each filter will operate it on its own, and eventually we get back a query object which will have all the right additions and joins or whatever we need to do the search for what the user has searched for. So here's an example of an implementation of an individual filter onto the free text. So we pass in the table alias and the field name. So for example, blog posts table. And the field title, we pass in blog posts and title. And then in the build query from method, this is where we have to check does it exist in the query string. So if request query this field name, we're basically saying query string, do you have the field that we're interested in, which in the example I just gave would also be saying, does the query string have a key title? And if so, what's the value? If it does have it, then we'll be able to decorate the query object by changing the web condition. So here we're just adding a like condition for our SQL. And then finally we can return the query back, so that the next part of the chain can create the query and so on. So this is really simple, really neat. This is what it looks like. Just add our new free text into the collection like that. But then we get a bug after we deployed. And the bug was, what if the user searches for 0? We had a specific use case where a user was searching for 0 and it was valid. This is like a statement. So this condition check failed.
いや、まだです。
Does this key exist? I.e., is it null? And if it exists, does it have a value? Or is it just an empty string? So we started changing all of our filter classes to have something that looked like this. As I was doing this, I just thought this doesn't feel right. This feels pretty glossy. And the reason for that is that this is a leaky abstraction. Filter classes shouldn't know anything about the way that KPHP's request class deals with the concept of keys existing in the query string. It all boils down to the fact that our filter class has a dependency on the request object, and that is not specific enough a type for our use case. So, the way that we approached this and fixed it was we recreated a new interface called search parameters, and we changed the signature of the filters to depend on the search parameters interface instead. As you can see, the search parameters interface has two methods: has, which returns a bool, and value, which returns the value of the thing in the query string if it's there. We can still use KPHP's request object. We can still use the query string. But instead, we can now wrap that up into this search parameters implementation. So here's what that would look like. We inject the request object in the constructor. Our has method wraps up that slightly logic about the implementation details of KPHP's handling of query strings. So now that's hidden away, we don't have to worry about it. Which just returns from the query method, as we were doing before. The revised filters look like this. This reads so much better, much more nicely than either of the previous two versions, which directly depended on the request object. It reads like plain English, doesn't it? This is something we strive for. Work is to try and write code which reads as much like plain English as we can. So instead of dealing with the internals of KPHP, it's now just dealing with a nice interface which is very specific to what it needs to do. Benefits here of adhering to interface segregation. Our classes are more loosely coupled. We've given our filter classes one less reason to change because it's no longer concerned with internal implementation details of the framework. And our filter class itself has moved towards being open to extension because it's dependent on a very specific interface. So if we want to change the way that we are sending in search parameters, let's say we want to use post instead of query string, or we want to use JSON data on an API call, or even if we want to make a command line tool, we can just create implementations of our interface. As PHP developers, I think it's easy to read the definition of the interface segregation principle and think of an interface like this one. Right? An interface is a thing in PHP. It's an abstract type providing a contract for our classes. But Ruby, for example, is an object-oriented language, fully object-oriented. Everything in the language in Ruby is an object. A string is just an object which has methods you can call. Arrays, booleans, the same. But Ruby, more object-oriented than PHP, doesn't have interfaces, doesn't have this. So how would a Ruby developer interpret ISP if they don't have a thing called interfaces? And the truth is that all classes have an interface, even if they don't explicitly implement one. So we go back to the IDA class from earlier. I'm not going to make the noise again, don't worry. You can see that at the top there's no implement keyword. It's not explicitly implementing an interface, but it does have an interface, and its interface is just its public methods and their signature, which would look something like this. So this interface doesn't exist, but you can, it's kind of an abstract idea. It's out there. So we can take this idea, and it leads really nicely into a point that Dan made in his talk, which is that ISP for PHP developers in particular isn't really about interfaces, but it's about types. Summed it up really well with a slide that looked a little like that. So let's quickly review what types are. Wikipedia helpfully tells us that a type is a classification of data which tells the compiler how the program intends to use the data. So in PHP, we've got complex types and we have scalar types. Now, I've slightly adapted that division because I think it fits this example more nicely. So I'm going to say PHP has objects and it has everything else. So in PHP, we have two types of object, really. We have abstract types and we have concrete types. So abstract are interfaces and abstract classes, and concretes are anything you can put the new keyword in front of and actually instantiate an instance of. So we've seen examples of interfaces like filter, abstract classes like duck, various concrete classes throughout this talk. And free text, for example, is a class which is of type free text, but it's also a subtype of filter, so it is a type filter as well. So in the other, in PHP, we have scalars and arrays. Arrays are technically in the complex type category, which is why I've had to adapt this slightly. I think there's some others that aren't on the list that I've missed out, but hopefully you get the general point. In PHP, we have objects which have methods that we can call, and then we have other types. In other languages, like Ruby that I mentioned in Scala, for example, they're free object-oriented languages. So everything in the language is an object you can instantiate and then call methods, even strings, bools, ints, etc. It would be returning an object of type array with methods. So if we go back to the point I made before, the interface segregation is about type specificity. Then we can say, well, if we're depending on an array has an interface, because it's a class and all classes have interfaces, we need to ask ourselves, is the interface of the class array specific enough for our use case? So that's what ISP is all about. So we don't have that luxury in PHP, we don't have these super amazing objects for everything, but we still apply that logic. And arrays, as I said, there's this bucket in PHP, there's this Swiss Army knife of programming that we can use to do whatever we want. And I would contend that maybe we shouldn't do that sometimes. So it's quite a common pattern to see arrays used for holding configuration values or options. So this is adapted from another real example we did at work, and we had a date picker method on our form helper, and the job of this method would be to render a date picker on a form. Right? Pretty straightforward functionality, pretty common functionality. And we had two arguments to the method, one which was called field name, which would just be the field name in the HTML, and then options, which would allow us to configure on the fly things like the CSS classes, or whether it's a required field or not, change the text label, that sort of thing. The problem with doing it like this is that in the class itself, in the method body, we've got to have code like this to check each option. We've got to check whether the key exists in the array or not, and then we've got to check the actual value of it. It doesn't read very nicely, it's pretty boring to type. It's also pretty prone to errors, particularly from the point of view of the calling code. So here in this example, in the calling code, I've deliberately misspelled is required field. When I run that code, I'm not going to get any error message. So the only time I'm going to realise it's not working is when I notice that the code's not doing what I want, and then I've got to start debugging and trying to work out why. And trying to spot this kind of thing is a massive pain, as I'm sure you are aware. We've also got no auto-completion support. I'm a pretty lazy coder. I really lean on my IDE and its auto-completion support, so I always want to have it wherever I can. So instead of using an array, we could use an object. We could use a class. So we can make a class called datePicker options, and then we can define each of the options we want in that class. So for example, is required field, which will default to false, and then we can turn that to true and false using set required field, and we have a getter method called is required field, which just returns the value of it. So by doing it like this, we add some constraints to our options as well, because now this can only be a boolean, whereas before someone, if they wanted to, could assign anything they like into that array, but now it has to be a boolean because we've got typing support. It's a string, and we can have validation. We've got set. For some bizarre reason, we wanted to make sure that our label was no longer than 25 characters. We can do that, and we get the complete support array. So this is what the revised version would look like. We're passing a datePicker options instance instead of the array. The now looks much nicer. It's easy to read, easier to reason about. You can look at that line, if options is required field, and you know exactly what it means. You don't have to parse array type stuff to work it out. And our calling code looks nicer as well. It's more declarative. It's easier to understand. It's expressive code. We can apply that logic to other primitive types as well. This isn't technically connected to ISP, but I think it's quite a nice little tip. It's quite common to see functions or method signatures which have lots of booleans for enabling or disabling certain things. This is adapted from something I've seen in the wild, so let's say this function is effectively a factory for an instance of connection, and you're going to call it and it'll give you a The problem here is that when we call the code, we've then got this horrendous line of boolean. When you go and look at that code in a week after you've forgotten what each of those mean, you're going to look at that and go, of course, right, it's starting to connect, true, false, true. Right. And it's not so bad here because we've got the function definition right above the function call, but in reality you're not going to have that. So it's really hard to reason about this code. So sometimes you might be working with a third-party library which has a function signature like that, and there's nothing you can actually do to improve it, but what you can do is you can wrap around it, you can adapt. So you can approach this problem using the builder pattern. So if we created a class, we pass in whatever we need as dependencies, and then we have methods called enable persist and disable persist. And those are just going to toggle the persist value between true and false. They're setters effectively, but we haven't used the word set in the method names because it reads nicer. And each method generator will return an instance of the same class, because we can then use fluent method chaining for making nice readable code. Now, there are other options in that function signature we had on the previous screen. We've got persist, enable awesomeness, disable flux capacitor. To fit them all on the screen, but you have to imagine that they're there as well. They've got a property and they've got enable and disable methods as well. And the most important part of this class is this function at the bottom, the get connections, and that's the part that wraps that original connect with those nasty booleans which are so hard to read. So we can wrap that function call in this method, and we're hiding the implementation detail of those booleans inside this class. So now our calling class, instead of calling the function, creates a connection factory, uses fluent interface, call methods and set whatever things we want to do, and then call get connection. This is many, many times nicer to read and easier to reason about than the function call. But yeah, we have more code, which, as I said, is something you find you have to do more of when you're writing better code. So, the final solid principle, and the D, is dependency inversion. Dependency inversion principle states that we should depend on abstractions, not concretions. Who has heard of dependency injection? Get quite a lot of hands. Dependency inversion, or the dependency inversion principle, is what we're trying to address when we use dependency injection. So when we say a class depends on abstractions, not concretions, we're talking about a class's dependencies, the things it needs to get its job done. This time I have adapted the constructor, and I have removed the and the arguments from its signature. So instead of passing in its dependencies, we're going to instantiate them in place. So we're finding out running duck, quacking duck, and flying duck do properties by using new. So this class is now dependent on concretions because they are, if you like, concreted in place. If we want to change the behaviours, we have to change the source code, right? Which, as we've seen in open close, is something we want to try and avoid. So we can adapt it and change it back to something like this, where in the constructor we're passing in arguments, we've got typeints, and then we're assigning to properties inside the constructor body. But what I want to note here is that in this example, we've got swimming duck, quacking duck, and flying duck as the typeints. Those are not the interfaces we created earlier. Those are the concrete classes. Those are things which can be instantiated with new, and indeed we saw that on the previous slide. But this class is now dependent on abstractions, even though it's dependent on concrete classes. Because from the point of view of this class, it doesn't know what swimming duck, quacking duck, and flying duck are. It doesn't know that they're concrete classes or whether they're interfaces. It just knows that they are types with methods that it can depend on. So if we want to change, swimming duck into an interface, for example, at a later time, we can do that, and we don't have to change this class. So dependency injection and managing dependency inversion principle is not necessarily about using interfaces. Like I said, we could change those concrete classes to be abstractions, to be abstract classes or interfaces if we wanted to in the future. But the point is the choice is now ours. It's not hardwired into that other class because it's dependent on abstract concepts. I think we've seen plenty of good examples in this talk of the value encoding to interfaces. But DI does not mean you always have to do it. As always, evaluate the pros and cons of each approach and make the appropriate choice for your use case. Dependency inversion is not necessarily about objects either. Go back to my examples of Ruby and Java as languages which are fully object-oriented. You can have a class which depends on strings or booleans or whatever. And in those languages, they're still dependent on objects. Just in PHP, they're not objects, they're scalars. So let's have an example. We have a class called MySQL Connection Factory. And in the constructor, we have the username and password for connecting to the database. These are concrete strings. This class is dependent on concretions because we can't change those strings without modifying the class. It's in breach of OCP and it's in breach of dependency inversion. A change of credential requires a change in the source code. So just like using dependency injection for objects, we can inject strings in from the outside as well. And here's what this would look like. We just change the constructor to pass in the values in the outside. And now it's up to us where we store those values. We can put them wherever we want. We can put them in a settings file. We can put them in environment variables. It's up to us. I said before that Solid tends to put more burden onto the calling code. And I think this is DI is a good example of that. So you can see like the bad version, though we're not using dependency injection and we're dependent on concretions, it's 2 words and a semicolon. But with dependency injection, we're having to do more. We have to wire stuff together. We're having to instantiate things and hook everything up. This is where a dependency injection container can help you. So there's several examples of DI containers in PHP. They include Pimple, Orin, PHP DI, Zen Service Manager. There's loads of others. If you want to know more about those, I would recommend going and reading their documentation. They're very powerful tools, DI containers. The trade-off for using them, in my experience, is that it can make your code flow a little hard to reason about. Because you take the logic of wiring things together and you put it somewhere else that you're then going to go and look if you want to work out what's going on. It's, I think, simplification through obfuscation. And it's a little bit like tidying your house by putting everything into the cupboard under the stairs. You just moved the burden somewhere else. So DI containers are a really useful tool for managing dependency injection, but you don't have to use one to do dependency injection, and you don't have to use one to comply with the dependency inversion principle either. There you go, you've got one more keynote and then we go to pass it. So, in summary, here are a few points that I ended up writing down after doing the research and writing this talk. We spend more time reading our code than writing, so we should... slides in a little while, which will have all of these handy links in if you want to go and read any more about it. And that is it. We've got time for that. I think we've got time for one question. Anyone's got any? Do I find more information on this? About Solid or all the slides or whatever? Wikipedia's a good start, Solid, and then there's an article about each individual principle, and there's loads of blog posts where people have written their interpretations of the rules. The Headfirst Design Patterns talks about each design pattern quite a lot, and he says this will help you meet this guideline, and it references Solid and stuff, so that's another really good resource. Okay, thank you very much, everyone. the editor and eventually came to own the experience of using C# and Visual Basic. And while I was there, I sort of carved out this little interesting position for myself, which is trying to figure out what Visual Studio will look like years from now. What is the future of Visual Studio? If we were going to make this programming thing better, if we were going to make programmers more efficient, what would it look like? And in order to answer that question, I managed to convince my superiors to let me do a study. So I did the, to my knowledge, only ever done end-to-end study of Visual Studio, where I sat behind a one-way mirror and watched people program and solve problems on a computer in a sort of very general set of tasks for a month and a half, right? And as a result of that, I gained a lot of sort of insight into what it means to program, what it means to be a good programmer, right? And how we actually do it. And this is important because as an industry, we're actually not very introspective. I love it. We have these guys who come in, I only use the keyboard. I never ever touch the mouse, right? When we have videotape of them using the mouse about half the time, right? It turns out that depending upon what tasks you're doing, what your mental processes are kind of doing at the time, you have different modes of operating, and one of those modes typically is done with a mouse, not a keyboard. And so I did this study and started to design what I thought the future of programming would kind of look like. Specifically tool-oriented, right? Like that was what I was tasked with. I wasn't looking so much at the languages or any of that, but somebody else's job that was. And so I built a bunch of interesting prototypes and stuff, and they've been slowly trickling out of Microsoft since then. But this is where I first started, right? I started at Microsoft on Visual Studio, imagining what programming will look like in 10 years, and I'm like, it will be really fast to write, right? That's kind of where I got to. And it will not only be really fast to write, but you'll be able to navigate really efficiently, right? These are the two things that I sort of latched onto. And that study also taught me something very important. And what that thing was led me to the next project, which was Lighttable. Right? And what that study taught me was that despite, as Fernando said, Visual Studio is a monument to humanity. It is 55 million lines of code when I was there 5 years ago, right? It's a gigantic piece of software. But in that study, I found out that most of the things that are in Visual Studio weren't actually helpful. They could have been. Like, they could have been useful. It wasn't that the features themselves weren't good, but they were dwarfed by the fact that everyone was playing computer inside of their head. This was how they came to understand the software that they were working with. This is how they came to understand programs they were unfamiliar with, even ones they were familiar with. When something goes wrong, like, your only action is read some code, imagine what the computer would do, right? And play it out in your head, write some stuff down, and just keep doing this over and over and over again until eventually you basically simulate the program and you found your error, right? The premise behind Lighttable was, what if we were directly connected, right? What if there was no time between change and result? What if we shortened the feedback loop to effectively nothing? And I think, there are many interesting ideas that you can Lighttable, but the one that people really latched onto was what I called at the time the insta-REPL. And the idea was you type code on the left-hand side, and if there was anything that ran as a result of that, on the right-hand side, you'd see the code filled in with all the values, right? So kind of zoom in on it, right? So, this isn't enclosures, so it's supposed to be syntax, but if I add 3 and 4, it shows me the answer is 7. And so I do some math, and then what's interesting is this def-end thing is a function, right? And so the function takes 2 arguments, and you can see they got filled in as well, and you can see what the result is. What this enabled was, as I typed, it did this. So I could watch the data flow through my program. Right? There was no question what was going on. When I said that people were forced to play the computer inside their head, what they were trying to do was make the program observable. Right? They were given this sort of opaque thing with a set of instructions explaining how it works. And the goal here was, let's just open the box and let you see inside of it. And that was really interesting, and it was useful, and there's lots of very neat things that came out of Lighttable. I mean, it had other ideas too. It had this sort of small talky notion of like, I'm going to put code, little snippets of code all over the place and embed running applications in it, so that I can sort of create my own organizations for code. Right? I'm not limited to just what I can put in a linear file. I can create this sort of canvas upon which all this stuff sits. So we did Lighttable, and one of the things we had sort of an explicit goal of, right, was not just unlike at Microsoft, where the goal was purely like make programmers more efficient. Our goal with Lighttable was actually, we want to make me more efficient. That's great, and all that has potentially huge economic value. But more importantly, we wanted to make programming more accessible. Right? One of the things that we came to was this idea that the reason programming is so hard is because it's unobservable. Because you can't see what's going on, you can't see the effects of change, you can't watch your data flow through, and so you're doing this replaying in your head. And Lighttable, with features like this, it was pretty good for programmers, actually. That study that I did for Visual Studio, we kind of replicated it with Lighttable to see what the difference was, right? And for a career programmer, hey, programming this way, it's much fast. And there were lots of interesting things that came out of that. For example, in Visual Studio, people would write large swaths of code before ever trying, before ever pressing the play button, basically. With this model, people wrote little tiny bits, right? And we're trying it all the time. And as a result of that, they built up, as they were building up sort of abstractions and all these functions and this sort of set of primitives, they knew what every single one of them was doing. They knew it worked correctly. They knew what their result was going to be. And so that was good. A career programmer could be nearly twice as fast. Turns out that twice as fast actually isn't enough. This is something that people have sort of a religious attachment to, right? These are our tools. These are the ways we express ourselves as programmers. And so 2x, while interesting and compelling, is not enough to get me to drop Emacs, right? It was not enough to get me to get out of Visual Studio, or whatever the case may be. So it didn't really get the sort of attention we had hoped for in that regard. Well, we got tens of thousands of people using it. More importantly, though, it did nothing for our other goal. Of making programming more accessible. And we tried to understand this. And that understanding resulted in an essay that I wrote a while back called Better Programming. And in it, I sort of realized that I would approach this problem. I used to say, I want to make programming better, right? And I realized I made a classic rookie mistake, which to this room is probably well known and understood. I tried to answer a question I didn't really understand, right? Like, what does making programming better mean? What is better? That implies that there's something wrong. What is wrong with programming? What even is programming, right? It's kind of an interesting question to start to ask. And so we started doing some research, we asked a bunch of people, built a bunch of prototypes, tried to sort of develop an understanding for what we were actually trying to do. And I sort of came to an answer about what is wrong with programming. If we're going to do anything to fix it, we had to have some notion of what it is we were actually fixing, right? And it came down to 3 properties. The first I basically already started to talk about, right? Because the programming is unobservable. I make some change in code, unless I manage to execute that code path, in manual clicking around on the screen or whatever, I have no idea what happened. And as I'm making the changes, if I make a whole bunch of them, I have no idea what the effect of each individual change is, much less the effect of the entire aggregate of changes. And this is a lot of what we were trying to address with Lighttable, was trying to make programming more observable. But there's another problem too, and that is that programming is indirect. So let's do something fun. If I'm describing a drone, right, and I have this thing hovering over here next to me, if I want to make that drone do something using pick any language you want, right, I have to first translate it into that language. I have to first translate it into the computer, right? I have to think like the computer in order to get the computer to do what I want. It's this very indirect mapping. And if you look at the vast majority of errors that happen when people program, they come from actually relatively simple translation errors. Right? It's this indirection that causes a lot of friction. So when you're doing that study on Visual Studio, we saw this over and over again, where somebody had the right solution, just along the way they just did it slightly incorrectly. And again, it doesn't that the logic was incorrect or any of that. It's just literally the mechanical process of translating that logic into Python or C# or whatever. It's easy. We're not very good at it as human beings. And the last one, and this is something that career programmers really latch onto when I talk to them, is that it is incidentally complex. What I mean by that is that the vast majority of what we do when we program has nothing to do with the problem we are trying to solve, right? A very, very simple demonstration of this is, I like to pick on how long does it take to set up a dev machine from scratch, right? I want people to take the better part of a week doing this at Microsoft. That's just to get code to run, right? That's not even trying to do anything interesting yet. That's just to get started to start your problem, right? And so when I say that the programming is incidentally complex, I mean that we spend a great deal of time solving the problems around solving our problem. So to give you a simple example of this, to sort of demonstrate exactly how hard programming really is, right? We tried to come up, we did this talk a while back where we went around and had a bunch of people try to build what we thought was one of the simplest possible programs you could imagine a normal person wanting to build, which is a button on the screen that counts the number of times it's been clicked, right? And so, I can click the button, it says 1 and 2 and 3 and that's it, right? If you think about this, like what it takes to build this little button, we'll assume you already understand HTML, which is a big jump, but we'll assume you know enough to write this little bit of HTML here. And then it's not so bad, right? It's just 6 lines of JavaScript. Well, let's unpack exactly what's in this 6 lines of JavaScript. So first off, you have to understand the notion of identity, which is arguably one of the hardest problems in programming, even though it seems like it should be something very simple. Now I have to tell the computer, hey, that button that I just put on the screen, I'm still talking about that button. I want to look at that one, right? You then have to do the scope, right? This again, 6 lines of code has a function in it, which is creating a scope, and things are weird in this sort of world. Things that you define there don't escape, but if you talked about them above there, they're ambiguously escaping. You have the notion of mutable assignment. That's majority programming errors are the result of mutable assignment. You have closures, something that still most career programmers don't understand correctly. You have asynchrony, which is probably unquestionably the hardest problem in programming at this point. You have objects and properties and the DOM. That 6 lines of code contains the context of years of work, right? You have to have spent years to understand what all of those things are doing. Yeah, sure, somebody might be able to Stack Overflow, copy some of this out and I have a button that works. But that means they can't change it because they don't understand it, right? Those 6 lines of code, I joke here, like too long didn't read for 6 lines. But that is kind of the reality, right? Programming is hard. The question is, does it have to be hard, right? Is this sort of intrinsic? My standpoint is no. But this is where we ended up with Light Table, right? We had taken this kind of language. We took JavaScript, we took Clojure, we took Python. We're like, well, if we remove the feedback loop, programming will be easy now, right? Because you don't have to put the computer in your head. But this didn't change. All of this is still true, right? All of this is still necessary. And so as a result of that, it didn't make things much better. And that's sort of the fundamental problem with trying to make it more accessible, right? Programming is still programming, no matter how good of a tool you make for it. And the problem with that is that these languages and these tools were built around the idea that we were going to build applications, right? That the end result of programming is a little icon that you double click on your screen and does one thing, and somebody writes it and they give it to you, and that's that. But the reality is what we really want, when I started to think more about what it meant to make programming more accessible, it wasn't about making applications. I mean, we struggled with this for a long time, right? We're like, we're going to build websites, we're going to make it easy to build websites, right? But it's actually to do something far more fundamental, right? It's just to think. Because fundamentally, if you go back to the beginning of 1960s when a lot of what is modern computing came to be, the idea back then wasn't these single-purpose appliances, right? The idea was a tool to think with. And if we're going to make programming more accessible, ultimately what we're trying to do is make a thinking tool, not necessarily a tool for building large-scale applications, right? Because at the end of the day, the computer is the greatest thinking tool ever developed, right? If I know the magic incantation, this is punch holes in this card, I can get the computer to think for me, right? And that is a hugely, hugely powerful thing. We went around pitching this to folks, we labeled it a superpower, because that is fundamentally what it is. It's one of the only times that given a computer, you can start with nothing else and create something of immense value, right? Just by knowing how to punch these holes. And so that's what sort of ultimately led us to this project that we're working on now. And that project's name is Eve. And then this idea, I started with Visual Studio trying to make programmers better. Realized that the tools are actually not all the problem, right? So like the model of programming itself is a problem. Not the idea like, hey, the feedback is now there, so that makes it observable, but it wasn't quite the way there. And it was still a tool, right? We're still pushing this from a tools perspective. Eve is, what would happen if we tried to solve this problem from the ground up, right? Ignoring basically everything that exists. What would you build if you could? If you could basically imagine building programming today, right? So the first approach to this, of course, as a programmer, was to take all the things we thought were good about programming, and all of the sort of trends that were happening, like functional programming, immutability, and all these things. We put them all in a pretty little package, and that's just going to work. So the first prototype of this was a thing that I showed at Strangeloop, which is a software conference. No, it's not playing. There it goes. It was a software conference that sort of like deals with a lot of the more interesting sort of avant-garde ways of thinking about the world. And so the idea was, we take functional programming and immutable data, and we will put it in something that looks a lot like a Jupyter notebook, right? And we'll make it something like really working with the data, right? I right-click on a thing, I tell it what I want to do with it, and you can see all the results. And don't get hung up because it doesn't look super great at this point. I built this prototype in like 4 days, but it was really interesting because it took a problem that would normally take quite a long time, the better part of a day, for example. So this was taking a bunch of data out of Mongo, doing some usage data out of Mongo, and then doing some map on it, and then getting the graph out of it, right? And all this again was done by this sort of like dragging and dropping and like clicking on some things. And there are a bunch of interesting ideas in this. One is the idea that you're always kind of working with the domain itself. So we'll see here in a second. When I want to write out some math, I actually do it in math. By that I mean mathematical notation. Zoom ahead here, because I'm apparently being slow. Right, so, I want to sum over all the x's and divide it by the number and ta-da, average, yay. So the idea is, like, if you're working in a domain, let's say, for example, I have my drone example again, right? If I'm working with a drone, there's a drone on the screen. Right? Instead of describing a set of operations that I'm performing, I just move the drone around, right? And it's capturing what those steps were. And then I can parameterize it by data or like get a chart or whatever I'm trying to do, right? So this is interesting. And we took a much better, much prettier, cleaned up version of this. We're like, this is awesome. We can build all sorts of things with it. Later in the video, I'll skip ahead. I show like building a website this way, where, you just have these tree of functions that do stuff. And it was interesting and cool as a programmer. It was very exciting. And I happened to be at the opening of Brett Victor's laboratory, CDG in San Francisco. And there were all of these non-programmers, brilliant people, physicists and mathematicians, and all these people there, done on a program. And we set, like I said, a much better version of this in front of them and like, try it. Right? We're like, we're stoked. This is done. This is going to be amazing. Anything in it, right? And I'll never forget the reactions we got, which is they were trying so hard, right? And they were very well-meaning. They genuinely wanted this to work, so they were willing to do things that most people probably would not really be willing to do. But there was this thing that surprised me, this thing that they started with. Out of all the things that I expected to find out in this, the hardest thing... And the reactions that we got were really obviously bad. So like, somebody would look at it and go, they had some data at the top of the function stack, and they had some calculation they wanted to do at the bottom of the stack, right? And they're like, I want this down here. And you're like, kind of look at it and you go, well, you can't, you'd have to pass that through all of these, and you can't really do that. And they're like, I don't understand. I see it, it's right there. Like, can I use it here, right? Well, okay, fine. If I can't do that, can I use this up there? No, you can't really do that either. We'd have to thread it through, going back up, right? It was like this really, I don't want to believe the arguments I was making, because we were trying to understand, like, well, scope is really important, right? Like, you need it for functions are really important, and I don't know, that's like something we can't do, right? And so we tried to do a bunch of things. We tried to make this nicer. We're like, okay, well, we'll make it look prettier. And we tried to do a bunch of things to make the scoping thing less of an issue. So there's no variable shadowing. We did a much simpler version of scope. We do arrows. We colored things the same. We tried to do all of these different things. Nothing worked. It seemed like it was kind of like just this fundamental problem that was really hard to get over. And so that led us down this very odd line of questioning, which is, well, if our first attempt at this, what the industry seems to think the future of programming is, like I said, functional and immutable, and yay. If that's not right, and scope is a kind of a problem which basically encompasses all of programming, where do we go from here, right? Like, what does it mean to remove scope from programming? So if you think about it, we have scope, can have functions, so that's already scary to begin with. But also is that when you're building up these like nested data structures that you have, they're creating scopes, right? You're starting to worry a lot about where something is in this tree of data, and you don't want to duplicate, because you put that data somewhere and you put it in another place, then they're going to be out of sync, and you have all these problems. There's another version of the scoping problem. So you can have functions, you can't really have data structures. You don't have data structures, you don't have anything that can keep things in order anymore. So you don't have ordering. So if you think about what programming is, if you ask a career programmer what programming is, they would probably say an ordered set of steps, typically executing functions with a set of data. All of that falls away if you remove scoping. And so we started to look into, well, has anything ever worked this way, right? And there is at least one massively successful example that works exactly like this. And that is Excel. Right, so Excel has a single data structure, but you don't work with the data structure directly. It has no scoping. If I can see a value, I can use it anywhere. It has no inherent ordering. It has scalar functions, but you're not nesting these deeply, right? You're writing out basically the equivalent of mathematical formula, and it never goes deep enough. So it has all these properties, and that is a fantastic result. And also a terrible result. But a fantastic result first. It's a fantastic result because 800 million people use Excel every single day. It is unquestionably the most accessible talked with some folks at a Fortune 500 company, right, in this cruise line. And they had this spreadsheet that was 10 gigs in size. It had been built up over a decade. No professional programmer had ever touched this spreadsheet. But it modeled the entirety of the Fortune 500 company's business. It could have moved every other system and run it off of this spreadsheet. Like, this is amazing, like, totally, utterly amazing. And so that's great. But at the same time, Excel is the ground. Excel isn't meant to do that kind of thing, right? So, there was a joke around it, like, we made any changes to the spreadsheet, we had to go to lunch. Because it took an hour and a half for it to propagate, right? And Excel is constrained, right? It's a two-dimensional grid of numbers. If your problem is not easily specified as a two-dimensional grid of numbers, kind of out of luck. So we looked a little bit more. And we found that there was one other case that worked this way. Again, massively successful. And that is relational databases. Relational databases have the same set of properties, right? They don't, if you can see a value, you can use it anywhere. If you can see a table, you can use it, barring access rules, basically. There's no inherent ordering, either to the code, the execution, any of it, right? Even the data has no inherent ordering. You order it as you will. And again, no like deeply nested functions or any of this crazy scope stuff going on. You just have basically functions and scalar values. And that is a great result, again. Certainly not accessible like Excel, but it solves the other side of the equation. It is a flexible thing, right? The world runs on relational databases. At the end of the day, basically every bit of data ends up in one of them. And we have built games and websites, all the things you couldn't imagine really building in Excel. So we discovered this, like, hey, relational databases is an interesting case. Let's see what people have been saying about them recently, right? There's got to be stuff other than Postgres out there that we can look into. And that's where we ended up on research out of here, actually. Joe Hierstein's lab, the Bloom Lab, had been working on a language called Bloom. And they were working on that language to do distributed systems. And the idea behind it was that it was a query language, so a little bit like SQL, but it was based on Datalog. If you know what Prolog is, it's kind of like Prolog's little cousin. It does a lot less and is a lot simpler and is able to be a lot faster as a result. And they were building distributed systems. They were like re-implemented Hadoop, right? And well, that's really amazing because it was orders of magnitude smaller and all these great things. Could we build a website this way, right? Like, could we take this, maybe stretch it a little bit, think about it in a slightly different way, and how far could we take it? So I built this prototype. It was ultimately actually the prototype we raised money on. And it's a very interesting thing because if you read what these little things do, we have an intuition, which is that Prolog, right, or Datalog, or any of these, is written in predicate logic. And predicate logic is totally hard to get your head around. But if you think about it, it kind of looks like fill-in-the-blank sentences, like those Mad Lib books we had when we were kids, right? It's like, put a color here. And if you squint and you think of it that way, if you think of these predicates that way, and you think of foreign clauses as like, when you see this thing, do this thing, you get this kind of very natural way of thinking about it. So this is the incrementer button, right? That little button I was talking about before. So like, well, when I'm setting defaults, remember that the counter is 0. And when the counter has a value, draw this button. And when that button is clicked, change the counter as whatever its current value is to the current to the value plus 1, right? And so like I said, we built, interesting things out of it. We always built UMVC because that's what everyone builds. But started building interesting things out of it. And we started to realize this crazy way of programming, that has no data structure, has no inherent ordering. When I built this prototype, originally didn't even have aggregation, which is interesting. Sort of made us realize that a lot of the things we think are fundamentally necessary for programming just aren't. You don't need them at all, actually. And so that's an interesting example because not only did we get this website, you could say, oh, well, that's a toy or whatever. The IDE that it was written in it. And I know a thing or two about building IDEs at this point. I built a few. Visual Studio is 55 million lines of code. Lighttable, which was far less than Visual Studio and was designed specifically to be as small as humanly possible, was over 10,000 lines of code. This was 600. We're talking about a totally different way of thinking about the world. Not only was it 600 lines, it was written in Greek, in a language that had no tools, that didn't even have aggregation, that had bugs in it, and we still managed to write this in a week. And so that is a tremendously awesome